diffusion equation. Starting now to look into the stability by looking at separate terms in the big nasty Navier-Stokes equation. And today I want to show you a different way when it comes to the stability. From the advection equation we found the CFL condition, Coulomb-Friedrich-Levy number should be smaller or equal to 1. For the diffusion equation we found this R, which is dt by dy squared, should be between 0 and 1/2. That should be the stability criteria. We found that one from the von Neumann stability analysis. So today let's have a look at stability, but a method I like to call max mean. I know some like to call it a positive coefficient method. And you find the theory here in 2.7. Here somewhere. Stability. So the method, very simple, goes as follows. So you have an expression for an unknown quantity. Typical here, this will be the unknown velocity, for instance, in your scheme, and then you pick the center point. That's normally the most efficient, most stable. But it will then be a function of a bunch of neighbors multiplied with coefficients a, 1, 2, and so on. And then we define the smallest one and the biggest one, x mean and x max, the biggest one of all the neighbors. Now, if we can show that the new one, the one we're going to find, is limited between these two quantities, then we are dead certain this is going to be stable. So this is what we are aiming for. X should be limited between the smallest one and the biggest one. Now, to prove that mathematically, we can do the following. If all these coefficients are positive, all of them are positive, then we can write it like this. We take the sum of all the coefficients multiplied with the smallest one, and here the biggest one also multiplied with the sum of all the coefficients. Then we know for a fact the new one is going to be in between here. Furthermore, another if all the sum of all these coefficients, if that one is 1, and strangely enough that happens quite frequently. The sum of all the coefficients is quite frequently 1. Well, then we have it. X is going to be bounded. Very easy indeed. So that's the philosophy behind this method. So let us try it on the different schemes that we had. Yeah, I've to write them up again. For the advection equation, it should be here somewhere. Here it is. The advection equation, time derivative plus constant velocity a0 time the space derivative equal to 0. So it's a linear one-dimensional version. Using an FTCS scheme, we got the following recipe. Ujn plus 1 equals center point. And then we had minus ground number multiplied with uj plus 1 and then minus uj minus 1. uj minus 1. C being the ground number, which then is my time step multiplied with the velocity divided by the cell length. So the philosophy that the CFL number should be smaller than 1 comes from sort of physical interpretation here. You should not move longer than 1 delta x during one time step. Then it should be stable. Okay, let's now look at this max mean stability method. You start with the sum of all the coefficients in this recipe here. What's all the coefficients? Well, I have 1 point here, uj. He has a coefficient 1. Then I have j plus 1. He has minus 1/2 c. And then finally I have minus there. I have uj minus 1. He has the coefficient plus 1/2 c. And the sum is 1. Okay, we can use the method. Sum of all coefficients is 1. Beautiful. That was the first if. The next if, all coefficients, write an a upside down, meaning for all coefficients should be bigger or equal to 0. That is now the demand for stability. And how do we look? You see, this is not possible. I have a single 1 here, he's always positive, and I have plus c/2 here. The c, well, he will be a positive number, positive delta t, a0, I can choose, let's say positive. Then this coefficient is going to be positive, but then this one is negative, and that's unavoidable. So here we have to conclude, no, this is not stable. It's not going to work. Even if I said a0 is negative, I could make him positive, but then this one is going to be negative. So one of them is going to be negative, either sign of a0. So this doesn't look too promising. What about the diffusion equation? Diffusion, there we had time derivative, and on the other side double derivative with respect to space. And there you have the recipe. The forward time central space scheme gave us the following stencil: uj n plus 1 equals, then we have an r multiplied with uj plus 1 n, and we have plus j minus 1 n, and finally 1 minus 2r multiplied with the center point uj. So this was the stencil, and here r was delta t by delta x or y, whatever, square. So now let's try again this max mean method. Take sum of all the coefficients. Sum of all the coefficients. For j plus 1, I have a coefficient r. For j minus 1, I have the same. And for uj, I have the coefficient 1 minus 2r. Again, sum is 1. Okay, we can use the method. Now the demand, all coefficients must be positive or equal to 0. Okay, well, the r itself is a coefficient, he's always positive. No doubt there. So these two coefficients, no problem. The question will be the last one. He has to be positive. Okay, but he is positive if R is smaller than 1/2, which is exactly the same stability criteria that we found from the von Neumann analysis. So here, not only did we find necessary criteria, we even found the sufficient criteria, the exact criteria. So you see, this method, fairly easy to use. And for simple equations, no problem, he will give you the correct answer. So don't waste time using all this Fourier thing or matrix methods. Use it easy, use it simple. Let's see if this is correct. Any questions to these two? That's okay? Here I have programmed the advection equation, and I choose just a time step here to see what happens. I have my A0 velocity set to 1, and I have an unknown signal, which then is mostly zeros, but in a certain range along the x-axis he has a value. So when I run this one, I get the initial state here. So here I have my space axis, x, and here I have my unknown quantity, u, whatever that is. It's a signal of some sort. So initially it is 0, and then a jump, and then here's the value 3, and then back to 0. Now the advection equation with a constant transport equation, A0, what he's going to do, or should do, is to take my signal and just move it as a stiff object, more or less, with a velocity A0. With my choice of delta t of 0.1, my CFL value is now 0.1, way above 1, which then should be the stability criteria, according to the CFL theory, you might say. But it doesn't really look so very promising, does it? So he is unconditionally unstable. I can try again. I can run with a smaller delta t. Add a 0 here and run again. Same problem. Now you get the same noise, just developing slower, but this is going to explode. So the CFL condition alone, no, that's not the entire truth when it comes to the advection equation. Obviously not. It's clearly rather unstable. And even if I go the other way, using a bigger delta t, I can set it to 1. Then the CFL is 1. So now I'm sort of on the level here, what I'm allowed to do. And no, it's not stable. So it doesn't help. That one was unconditionally unstable. Then I tried the diffusion equation. So here I started initially with a very small time step. The problem at hand is now startup of a cuvette flow. So at time equal 0, my bottom wall then stands still and the top wall stands still, but t equals 0, he starts to move with a constant velocity. So initially my velocity field, the velocity profile is 0. And I know what I should get in the end, the steady state cuvette solution. The delta t I chose I chose so that this parameter r is now just 1/2. That's just on the limit. So this should be stable, just about. And as you see, yeah, it actually looks quite nice. And we should find then the steady state roughly at a time scale of 1. Remember, we have non-dimensionalized the equation, and that is indeed the case. When the time, non-dimensional time is 1, yeah, then you have roughly the steady state. Just now to check this stability limit, 1/2. How serious is it? Is it really the sufficient criteria that we have found? Or is it, cross that one, or is it just a necessary criteria? Necessary meaning you are dead certain it's stable, but you may even have a larger delta t in it, it can still be stable. But the sufficient criteria, that's exact. So now I'll go just a little bit above the limit here. So now I have an r which is not smaller than 1/2. It's a little bit bigger. So now let's see what happens. Starts out fine, but then he gets rather shaky. So yes, he's also going to explode. Better stop him. So here it was okay. The stability criteria, the sufficient one, that is 1/2. Yes, it is. No problem there. This one you have now been given. I won't go through this version of it. You have the same in this compendium as well. Here, after finding the max-min method or the positive criteria method, we use it on the entire Navier-Stokes in one swoop. It's possible, a little messy, but yes, it is actually possible to do it. Here I also use the Struwel number, so it's a non-dimensional version. Furthermore, I have cheated. Remember, it must be a linear equation, and Navier-Stokes is not linear. So I say this is for a generic velocity component W, where now W should be either the velocity in the x direction or the y direction. But that means W should either be U or V. But then these convective terms will be nonlinear. I can't have that. I have to linearize them. So I sort of cheat and say this W, which is either U or V, is something totally different than these U and V's, which is a lie. But we have to do something to make this run. The function F, meaning here the pressure gradient, and maybe even gravity, driving force, whatever, inside there. Now use the FTCS scheme on this one. Straightforward. Central space ready with everything, and you will have something like this. And you can rewrite it on the form. The new one should be n+1 here, equals, and then all the neighbors. This is in 2 dimensions, so it will be a 5-point discretization star. You need 3 points in the x direction to make a double derivative and a single derivative. Same in the y direction, so you'll have 5 points. Meaning we have 5 coefficients, all the square brackets. And again, if you add all these 5 square brackets, you get 1. Hence you can use the method. And then the demand, all these brackets should be positive. Well, that gives a little algebra, but you end up with something like this. And we only, strangely enough, get one demand for the time step. Here we have another type of demand, but the delta t doesn't enter into the equations. That's something we haven't seen yet. We'll come back to that. So it's actually a demand for spatial resolution. Delta x has to be smaller than something with the Reynolds numbers. Same goes with the delta y. That's not what I wanted. I wanted a stability criteria for delta t, only delta t. So I can rewrite these, and now I use the Courant-Friedrich-Levy condition sort of to exchange the demand for delta x to achieve a demand for delta t instead. So it's a sort of neat trick. And then I end up with 3 separate demands for stability for the time step. So the first one, that was the Courant-Friedrich-Levy condition. And here, the delta x and the velocity then has to be the local velocity. This means you should investigate these CFL conditions for every cell, for every time step. Because, I mean, this can change. You can't evaluate this one once and for all. So this one can be a little bit tricky. If you have sort of, you have a large inlet into a couple of walls, which then narrows down to a very small opening, you will get very high velocities in that opening. And typically when you do a numerical study, then you will use a lot of small cells inside that narrow region. So there the delta x and the delta y is going to be very small, but the velocities are going to be big. Then you're in trouble. Then delta t has to be very, very, very small. So this should be investigated during the simulation for all cells. Now, the second demand comes then from the diffusion equation. So we did this one only in 1D, so in 2D, a little bit more complex coefficient there. Now, this demand can be calculated before you start. So here you get an idea what delta t has to be smaller than. So this is also then listed in the SOLA code. And it says something about diffusion that we must sort of take into account diffusion from the neighbors that enters into your cell. So if you have something momentum from not just the neighbor cell but even the far neighbor, then that one also should be into your equation system. The last one comes then from the Navier-Stokes directly, here with the max-min method. He ensures a net positive diffusion. We are going to see more of this diffusion mechanisms that we have in computational fluid dynamics, because we have a lot of them. Diffusion, that means viscosity. But we have other mechanisms here as well. We can have force diffusion, and we can have artificial diffusion, we can have turbulent diffusion, and so on. So we have a look into that. But a diffusion, what does it do physically? Diffusion means if you have a jump in a quantity, jump in velocity or anything, diffusion will soften that gradient out. It will smear it out. If you have negative diffusion, you get the opposite effect. A jump will be increased. It's going to blow up. So the total diffusion, of course, has to be positive to make it stable. So these are the 3 stability criteria listed in the SOLA code that you have been given. Quick and dirty way how to find it using this max-min method. So yes, it is possible actually to use it on the entire Navier-Stokes.
Is there a simple argument why the sum of the coefficients may not be less than 1, but above 0, because then you will bound it by 0 below, and you will bound it by upper limit as well.
No, you can't say that, because if you have the sum something different from 1, then the initial theory here breaks down. If the sum is 1, fairly easy to see, yes, you get this expression. But now if the sum of the coefficients here and here is something else, then he will either be on the wrong side of x mean or the wrong side of x max. He's not bounded anymore.
But as long as all the coefficients are positive, and the sum of them are less than 1,
yeah,
then it will either, then you could always say that it will be below x max, but it may go 10 to 0.
Yeah, let's see, he should then still be bounded here, yes.
Maybe x mean will be negative, then you will have a problem, of course. That may be the case.
Yeah, still I think you can do it, but I think you have another problem there. If the sum of your coefficient is less than 1, I think you will end up with your unknowns going towards 0. They will die out.
Okay, maybe
they will disappear. So then I would think your original discrete version is not consistent anymore.
Okay, yeah.
So, because this sum equals 1 happens fairly frequently for most, at least for the FTCS schemes. For more complex schemes, it can be tricky to find anything useful with this method whatsoever. So then you have to use more advanced methods. But this happens so frequently that I think it's nice to know it. And it's so easy to use, I mean, you can take it directly from your head. So, yeah, you must use it with care, but when it works, then you are dead certain this is going to be stable. But as you sort of also are implying there, it might be stable for combinations where this is not the case. Maybe some of them are negative. It can still be stable. You can't really say that with this method. So it can only find what we call then the necessary criteria. If it works, then you are quite certain this will be stable, but it could still work without this method saying it's okay. Other questions?
When
Yep.
you say x mean or the x max,
Yeah.
is it the absolute of the elements or just the raw values?
No, you take plus or minuses, that's okay. It can be negative. So that's okay. Still has to be bounded. That's the whole point. The new one should be between the smallest one and the biggest one, then you are certain this is going to be stable. That's all. But if this one is negative, that's quite okay. It's still bounded. Okay, that was this one. Yeah, I have some notes at the end here for the one that we have used in the Sura algorithm. And a final point. This is also something we are going to look into quite soon. This spatial demand that we got somewhere up here. Yeah, we had to use a trick here. We had to use the CFL condition to rewrite it, not a demand for delta x by the delta and demand for delta t. If we had kept it, we would have had a demand that the cell Reynolds number, that's a Reynolds number based on the local quantities inside your cell, local velocity, and the length scale is then the size of your cell. If this cell Reynolds number is bigger than 2, you're in trouble. That is sort of a gospel when you have a steady state situation. What we are going to show is that if you have a transient code, then you can work your way around cell Reynolds number bigger than 2 if you have a small delta t. Here the c is then the CFL number. So you can have a small delta t and still have a big cell Reynolds number. So I'll show you this one later on. For now we jump further and have another peek at this advection equation. That one was unconditionally unstable. He exploded no matter what you did using the FTCS scheme, and we found that by using the max-min method, which you now can see here. You don't have to write anything actually, you can tell it directly from the scheme. The coefficient will be 1, and then minus CFL half plus CFL half. The sum is 1, you can use the method. Then the demand, all coefficients positive. No, that's not possible here. So using FTCS scheme on the advection equation will result in unconditionally unstable. So here I have just shown it with the von Neumann method, pushing in one arbitrary anode. He added from an arbitrary Fourier mode, and do some algebra, and you will end up with an amplification factor which is going to be bigger than 1 no matter what you do. Hence, the solution is going to blow up. So what do? We cheat again. First order upwind scheme. That is a famous one. First order upwind, then the philosophy goes as follows. The time derivative is as before, first order in time, forward Euler, but the spatial discretization here, it's now changed. This is now actually a backward difference. Here I have decided my velocity, A0, is a positive velocity. Hence the information will be traveling to the right here. So when I have to put in something for the derivative, the spatial derivative here, I now choose the center point minus the point upstream against the velocity A0. So now these 3 points will be my discretization star. Going from time level n to n plus 1, I only use these 2 points. So I need the old one here in the time derivative. But for the spatial discretization, I create a derivative among these 2. So actually, if you think in terms of central space differencing, then you have a a second order accurate derivative here in between these 2 points. But since the information sort of is moving to the right, then it should be reasonable to say that for the solution here, then we should find most of the information upstream, since it's going to travel to the right. So for the old values, I will take something to the left, meaning the upwind or upstream direction. So that's the philosophy. So the only change from the central space discretization, we had j plus 1, and we had divided by 2 delta x's. That's the only difference. So the price we pay is 1 order of accuracy. So here we should read plus the order of delta t and delta x. The previous version, central space, that was order delta x squared. That was a second order accurate. So now is the question, will this help? Well, here again I did von Neumann, and as you see, von Neumann involves a lot of algebra, but actually I got the CFL criteria out of von Neumann to ensure that the amplification factor G should be smaller or equal 1. So can we do now the max-mean method? Should we try it directly without pen and paper? First, what's the sum of the coefficient? Here is 1. For this one is, what's now? These two are the same. So what's the coefficient between uj, in front of uj? Well, that will be 1 minus CFL. So that's one coefficient, 1 minus CFL. But for j minus 1, you will have plus CFL. Sum of coefficient is 1. Yes, you can use the method. And then the demand, all coefficients positive. Well, the CFL alone is positive. And in front of uj, you had 1 minus CFL. Okay, there you have it. The demand, the CFL must be a number between 0 and 1. Then he should be stable. Let's see if that is the case. Go back to the advection equation here. So this one was the problem we had here, and it blew up with the central space scheme. So now I changed the scheme to something else. I choose first order upwind. And I choose, well, we can start with 0.1. So now it's first order upwind scheme, and my Courant number is 0.1. Should be between 0 and 1, so now it should be stable. Yeah, it is stable, but at a certain price. The correct solution is the red square box. He shouldn't destroy it like this. So what he actually has done, he has smeared out this sharp gradient that we had initially and created something quite different. So now we can try using even smaller time steps and see if it helps. Say 0.01. So now my Courant number is very small, 1 over 100. But you see it doesn't help. He still smears it out, destroys my nice sharp gradients that I had initially. So it's quite, what should we call it? We have a diffusion mechanisms here that we haven't asked for. He smears out this sharp gradient, and I shouldn't do that. You should just move it. So what physically has happened, we have gotten some viscosity into the problem, which shouldn't be there. So yes, it is stable, but at a certain price. And you can choose a small time step as you like, it doesn't help. What, strangely enough, does help if you go the other way. Now I have a big time step. And my CFL is now on the limit. It's 1. Now see what happens. There you have it. So yes, it's possible to find a correct solution here numerically. But then we had to do something rather strange. We had to use a very big delta T, as big as possible. Then he just moves it quite stiff. Why? Well, you can actually see that from the recipe we had here. Set the CFL number to be 1. So what happens? You have uj minus uj. He disappears. And the solution, my new velocity equals the old velocity at point j minus 1. Now we are actually solving this one using hyperbolic techniques. That was actually not my intention. So let's see, we have the advection equation there. So here I have x point j here, and I have j minus 1 here, and j plus 1 here, and time, level n, and here I have level n plus 1. So those 4 points, that was the original FTCS scheme that we had here. And that one didn't work, it blew up. So then we changed it, we did it like this, and said, since A0 here is positive, things is moving to the right, then I create a derivative in between these 2 points and say he should be responsible for the information up here. So I only have these 3 points into my discretization star. But this equation here was a hyperbolic equation, hyper, and the characteristics was dx dt equal to plus or minus a0. Now I only have one positive value for a0, meaning my characteristics is going to go like this. And then if you adjust your time step, so you hit exactly a0 on the slope here, then this characteristic line will sort of join these 2 points directly. Then you have solved this problem using hyperbolic techniques. So that's sort of a separate topic. We are not going to dive too much into it. But with hyperbolic equations, what you can do, or try to do often, is you rewrite them in the direction of the characteristic lines. Then a partial differential equation will be transformed into ordinary differential equations, which can very easily be solved. So you solve it along the characteristic lines, and that's actually what we are doing if you choose delta t so big that the CFL number becomes 1. Then you find a solution directly. So interesting, but for us not important, because of course in the end now we are looking at an equation looking something like this. First of all, it's going to be nonlinear. And finally, we are going to have some viscosity on the other side anyway. So we are not going to deal with hyperbolic problems here. Now this viscous term at the end, we don't have it here, it should be 0. So then it was a question, this upstream technique, well, he sort of added some diffusion. He added this, not this term, but say this effect from such a term. We are going to investigate also why. So it's possible to see it actually as an equation, which also then is something we will search for.
Excuse me?
Yep.
If we choose the discretization method like the forward, and it's, I mean downwind, then if it's stable, then it should be considered the lower limit for stability?
You mean not using this point, but using this point instead?
Yeah.
That would be here a very, very bad idea. Try it. Try it. What will you get? You will get something like uj n plus 1 equals uj n, and then you will have minus and then comes the C, and then we make a derivative, which now will be the difference between these 2 points. So that will then be uj minus, no, sorry, j plus 1 minus uj, and n. Now this will be the stencil, if you do it like that, as a downstream, not an upwind, but a downwind discretization scheme. So what you get here, uj, n, you will have 1 plus c. Now that looks promising, but what do you get in front of j plus 1? You will have a minus c. So he is negative, and that's unavoidable. He's going to blow up no matter what you do. Unconditionally unstable. So no, it doesn't work. Come up with a different idea. Other questions? Then we take a break.